So to have a really moving current, you would need that this thing became a complex. Okay, so far, in this case, f starts to be a complex number. So for what I was discussing, that f is a function of r, but it's a complex function. Okay? Yeah. So then you need that f starts to be complex. Not only real values.
So what confusing is about the supercurrent will be decayed.
Yeah.
And then inside the bulk, it should be 0.
Yeah, it should be 0 because the value of a as a complex number will more and more be 1, which is a real value. And if it's a real value, then
so that's it. How we.
But you can, this thing, gradient of E and R are compensating each other. So this is a gauge invariant thing. If it will start to be the constant, but the gradient of phase and R are playing such that it will be 0.
Okay, even though the f is constant.
Yeah, even though it's constant, but the phase of f is constant.
Okay. I see.
Yeah, maybe I could explain it better, but that's good because I'm getting feedback and I can.
Thank you.
Okay, good.
So first you suppose assumption that you get
Which is 0, which is the maximum concentration of the two parameters. You cannot have more. You cannot have more than these values.
then you suppose the other
Every other
situation will be.
I will always take this as a maximum times some f. So the meaning of f is the concentration divided by maximum concentration.
So here then you only consider the combination.
Yeah, I consider no magnetic field vector combination.
But I don't understand how to get this equation.
Complete which ones? Like you just substitute it?
No, I knew you are rewriting the equation that become this term, but how can you know that this is the coherent?
This is the name. You definitely see that there is some parameter in the theory which has a dimension of length. This thing is just constructed from the fundamental constant, mass, and alpha. Alpha was some phenomenological parameter.
But do you know the physical meaning that you knew it means the healing?
Yeah, that's I was trying to show that when you solve this equation, in this limit, that you are looking that f is not so far difference from 1, then we see how that epsilon x is changing with the position.
So here,
and we see that it's going like that.
So here is we are at a situation that is closing.
It's close to this value. Close to this value.
But still has some perturbation.
Yeah, it's some perturbation. Yeah, and this perturbation depends on things.
Oh.
And we are looking how it's recovering from this perturbation.
Oh.
And we derive the equation. So what we did, what I'm doing here is, okay, this is the complicated equation, real complicated, and I am using this assumption, and I am linearizing it. So this term, I'm just taking the only things which are linear in epsilon. I am not taking into account non-linear. Okay? And then it's easy to solve. And I am saying that from this equation, it comes out how the epsilon is different from the x. This is there is this fundamental characteristic on this side. And we are saying like, oh, that I was like taking, like if you're taking the things, you can perturb it here, or you can look far away here, how it's returning to the original value. In this region, it is like exponentially recovering. Okay, maybe. Do you understand what I mean? So here it does not apply, because here is the perturbation very big. But coming to the end, it's already not. Or if you would be able to imagine the water bath, if you put the water, then you are able to. But if you will take the mercury, you will be able to put your finger, not your finger to the mercury, and you will deform it. So the surface of the mercury will be deformed of the liquid metal, and you will see that here it's exponentially approaching the original level. So, okay. You have a question?
No,
I just need the answers. I hope that people come with answers, not questions. Okay, what was your question?
So the explanation I think I mean the theta is a function of r, right?
Theta. Yes. Theta is function of r.
他们差一个外加值。
So what was the question?
Just only this one.
那个差是你加的。
And later, I put this. No, you need to later you have to carry this one.
Okay, I need to carry it.
Yeah. And for the computer space, I heard someone says it's related to the Cooper pairs
Distance.
size.
Yes,
or distance.
yes. But this you can see only from microscopic theory.
Okay.
Yeah, but the coherent length, but the distance of the Cooper pair and the coherent length, this is the something what is called Ginsburg-London coherent length.
Yes.
And this characteristic distance of the Cooper pair is proportional to it. There's some constant amount of t or something like that. So it's not directly one-to-one. There is some numerical prefactor.
Okay.
Okay. But they just get it from the equations. So they realize the superconducting condensate should have some characteristic length. So they didn't know what is it. Only PCS guys they said it's a distance, average distance between electrons in the Cooper pair. But they already get some phenomenology about it before knowing the microscopic theory, which I look very, very interesting.
Okay. 1GL equation don't add it just consider A and the side.
Yeah.
But why no
The picture is hidden there.
Oh,
This coefficient alpha.
okay.
It's also hidden, in reality, it's also hidden the coefficient beta. Yeah, so temperature would be hidden there. But you need to know them, like this is like, you need to know it from your material. Okay?
What's the deal?
Well, like the different superconductors will have different alpha and different beta as a function of temperature. There will be slight difference. Okay? Maybe I can start on the methods on the membrane. So now I want to, may I, you think? Can I start? Okay, so I will now solve the one standard problem, and this is fantastic that the Ginsburg-Lambda theory predicts something what people measured, and this is the proximity effect. So now I have a situation, just to imagine that I'm imagining the situation that this is the interface, and on that side for X positive, here is the superconducting material here, and here for X negative, I am assuming that there is a normal metal, N. But it's a metal, it's not a vacuum, okay? So this is a metal, and this is the superconductor, which is also the metal. And we are looking how the order parameter will behave on such interface. That's the question. Important thing here is there are free electrons here. Okay, not vacuum. In vacuum we don't have anything, okay? And then naively you can expect that, okay, if psi psi originally lives just here. It's an order parameter. But we always interpret it as a concentration of the Cooper pairs. Okay? So we interpret it as some concentration of the Cooper pairs. So if I have some Cooper pairs, I'm just drawing them. These Cooper pairs are living here. It's a quantum mechanical object that you know from quantum mechanics that there is a tunneling. That things in quantum mechanics are prone to tunnel. So you can naively expect that the order parameter nearer to the interface will behave a little bit different. So it would be decreasing because some Cooper pairs will tunnel to the normal metal. They will dissociate it in the normal metal. So we will have less Cooper pairs. On the other side, there are non-superconducting electrons which can diffuse here and lower the concentration of the Cooper pairs, right? So it's like the interface process that Cooper pairs go from the superconductor to normal metal and normal electrons are coming on that side. So there will be the change of that. And we would like to know how, okay? So this tells you that, okay, some superconducting properties can appear in small part near to the superconductor. Okay? And this thing is called the proximity effect. That you put something to the neighboring and then you start to share or you get some small properties of someone like that. Okay? Did you get me?
Yes.
Okay. So let's do it. So we are going to solve this problem. And that's why I just want to tell you that we are also solving these things that if there would be vacuum, then we derive the boundary condition. So we would require, if there will be really vacuum here, not free metal, then I need to solve the Ginzburg-Lambda equation with these boundary conditions. But because I am in the metal, then this condition is relaxed. Okay, that's the physical argument is because I can have a tunneling, so the Cooper pair can tunnel. I derive it before to the vacuum. Okay, so that's why we got this equation. So I am relaxing this condition. So, and the solution is standard quantum mechanics, and I want to show you because there is a beautiful mathematics and we can really show it. So, in the superconductor, I need to solve this equation. No magnetic field here, okay? Situation happens, I take superconductor, normal metal, I put them next to each other, no magnetic field, okay? So the first Ginzburg-Lambda equation looks like this. And I'm already writing in this dimensionless form, okay? So I need to solve it. But now I really need to solve it here. And I really need to solve it including the cubic term. Before, I was making linearization in this healing length. Now I will not make this approximation. Okay? So let's do it. What? Well, because I now allow a big perturbation. Before I was saying, assume it's perturbed here, but I'm considering far away, or I can say perturbation is very, very small. And now I'm not assuming that, okay? Good. So let's do it. So I'm just writing this equation. And this equation is second order differential equation and it's a nonlinear. It's not so easy to solve, okay? But in this happily case, we will be able to do it. And the standard trick, which is very often used in the superconductivity, especially if you can treat the system one-dimensional. Basically, I am assuming that my order parameters psi is just the function of x. So I'm assuming that you know in the epsilon direction and z direction, it's like a big wall, like semi-space. So nothing depends on the x, and I'm just looking what changes from this direction to this direction. Okay? As we had, for example, when we discussed the screening effect, London effect. I also was assuming that there is not epsilon and z dependence. Like we are having this, do you understand me? Semi-space, okay? And these I am writing as my psi 0, which is a constant, times f, which is a function of x. No magnetic field, I am even assuming that f is a real valued function. In principle, f can be complex valued function, but I'm assuming it's a real valued function, okay? And now I'm making the trick. I take this equation and I multiply this equation by the first derivative. Okay? So what happens if I multiply it with the first derivative? I'm just repeating, and this is appearing the first derivative, and I'm not just this term, and I'm getting the first derivative here. Everybody see? And now the magic is that if I look a little bit closer to this expression, I see that, oh, this is nothing else as the total derivative of such expression. And if I look here, then I see, oh, this is like the total derivative of this expression. You see it? Have a look. David is seeing it. Is there anyone who doesn't see? Is it clear? So we multiply and just that, which is very good because now I see that there is a total derivative here and total derivative here. So I know the things is the same thing a part of the constant, right? So I can easily integrate it. And here I am just getting some constant on the right hand side. If the derivatives are equal, it means the original values are not equal. They can be different maximally by a constant. Okay? Great. So I am getting this. But look, guys, what I get. This trick helps me because I converted the second order differential equation to the first order differential equation, which means I simplify it. Okay? I can just rewrite it like that. I just put some constant here, multiply by 2. Okay, I just bring it into that form. Okay? So what is the problem? We need to find the value of the C tilde. Because it's still not defined. But it's very easy because I know from physical constraint that, okay, near the interface, here can happen whatever, and we will find what, but I'm expecting that if I'm going more and more to the bulk of the superconductor, then the order parameter is going to 1. And far away of the superconductor, I don't expect that interface will break it. Okay? So if I'm going with x to the infinity, I'm expecting that f is going to 1, okay? Far away. And this equation should be satisfied everywhere in the superconductor, also in the interface and also at the bulk. Right? Nothing else. So I can plug it. So if f is 1, then this term is not here. And if f is 1, then I'm seeing that, okay, this is minus 1/2, so I'm seeing that C tilde is minus 1/2. Okay? Because I am able to satisfy this equation, or this is the physical equation which should be, so we get it like that. Clear? Good. So now I got the following differential equation. That minus c squared is equal to this minus 1/2, and I put the other guys on the other side. Yeah, so there was the original thing, and I just put them on the other side. Okay, so you see it here. Now I put here minus 1/2. And I'm just putting this guy and this guy on the other side, taking minus 1/2 out, and I'm just a little bit looking and say, wow, super good. It's f squared minus 1 squared. Oh, even I wrote it like that because, okay. But it's clear, right? Good. So now you see, multiply by 2, even I write, oh, wow, okay, great, multiply by 2. Okay, basically what I just want to write you that from this differential equation, we immediately are getting that minus and minus cancel each other, and I can take a square root, and then I'm getting two solutions, plus and minus this thing, okay? But only physical solution is the solution with plus, because derivative, you see, I perturb here, but if it's going here, 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 the derivative is positive. So only positive derivative has a physical sense. Okay? So out of those two solutions, I am just continuing with the plus one because this is a physical. Okay, doc? Clear? Okay, so I get the differential equation like df over 1 minus f squared is equal to dx over square root of x times psi. Guta? I'm just now integrating. Okay. Here I am recognizing that this is arcus tangens hyperbolic. And the integral of that is super easy, and this is the integration constant. Yeah, if I'm integrating over x, I'm just getting this minus some constant, psi 0. So this is the solution for x equal 1. x larger than 0 in the S region, okay? So if I am now applying the inverse arctange, I am getting that fx is tan hyperbolicus of this guy. Okay, doc? So we still need to specify the constant x0 later. But the solution is almost fine apart of the x0, okay? Clear to everyone? Beautiful, isn't it? Perfect. So the things which we are seeing, like how the tangent hyperbolic looks like, so the graph of the tangent hyperbolic is something, I don't know, it's 0, yeah, and it's going like that. It's a constant and it's going something like that. So this is the tangent hyperbolic as a function of x. Looks like this, and we see there is some shift. So this tangent hyperbolic would be somehow shifted, we see, depending on the x0. Yeah, x0 is just shifting it. And this thing is a little bit rescaling it. I'm not showing it in the graph. Okay? So this is roughly the solution. I just want to remind you that this equation, which we are just solving, this is this equation. This is appearing in the physics very often time in the correlated system. For example, in solitons, we will also get equation of that form. And then normally the domain walls in some materials are described by this solution, okay? So the people learn how to solve this equation, and I just presented the solution. So it's always done in that way. We can only do this if C tilde is equal to -1/2. If it's not, then you cannot make this trick. Okay, so it's a very lucky thing that this guy is -1/2. Okay, good. So this is done, and now let's look solution for the normal state. So in the normal state, I am looking solution here, in this part. And since it's a normal metal, I am assuming that the order parameter will not be very large. Because in normal metal, superconductivity is not normally existing, but because the normal metal is close to the superconductor, it's in its proximity, we can believe that something is leaking in, but this leakage will not be dramatic, it will not be very large. This is physical assumption which I am making. Okay? So I am again solving the same equation, but I am directly ignoring this cubic term. Because I am saying that psi in the superconductor would not be large. Okay? I'm just ignoring this term. By this physical requirement. Clear why I'm doing it? Okay? And one thing, in the superconductor there was a minus, and in the normal metal there is a plus. Yeah, okay, but I had it written like in the superconductor there would be the minus if I would have it. And the reason for that is that coefficient alpha in the normal metal should be positive because it's not superconducting. Otherwise, it would become a superconductor itself. Okay? Lydia, do you agree? Okay, so that's why there is a number of psi. Okay, and I can also write it, and instead of psi superconducting, I would have some psi normal metal. It would have the same form. Okay, but I would have a sign plus. Okay, but that's fantastic because this equation is even simpler, and we immediately know the solution that it is some exponent times something. And there are again two solutions, but we are assuming that the wave function is decreasing, not increasing. So we are just picking the solution with this one, okay? Keep in mind, my x is a negative. I am solving it in the n region. So I need to take this solution, not the opposite one, okay? Clear? Good. So now I have a solutions, and now I want to match it. And the matching is like that. So it's a quantum mechanics. So I would expect that wave function in the right-hand side, which is in the superconductor, and the wave function in the left-hand side, which is the normal metal, should be continuous on the interface, including the first derivatives. If I'm just dividing this equation by this equation, this means that derivative of that and the derivative of that divided by that should be equal, and this is very easy to calculate this derivative because this is 1 over Cn. I'm just telling you that the ratio of these things is like this, okay? These things comes directly from this equation. And now you have formula for F, we have formula for Xi, and there are two unknown constants. First unknown constant is this value of Xi0, and the second unknown constant is this prefactor A. But I have two equations. I can solve it, and I'm just showing you the solution. So the solution is like that the A is given like this, and Xi 0 is given like this. Okay, you need to plug it and play and do some mathematics, which is, let's say, interesting but boring. This class is not about the mathematics, but you are able to solve it, okay? And you see the A depends on the ratio between Xi and Xin plus something, and we will get that there are several solutions. The second could be here a minus sign, but because of the physical reason, A should be positive. So I'm just picking this solution, and Xi 0 is like that. So we are really seeing that Xi 0 is like a negative thing, which really means I am shifting the order parameter like that. So the profile, no, Xi is negative. So I'm, and in my, okay, just to explain you, my solution was looking like that it is a tangent, and there is x minus x0, and there was this square root of 2 times xi. And I got now that Xi 0 is negative. You see it there. So we see that the tangent hyperbolicus is shifting from the interface to this direction, something like that. Yeah, so the solution will look like this, and from that point it's going like the exponential. Okay, so this is how the solution would look like of the superconducting order parameter. Yeah? So you see that on the characteristic length scale of Xi n, you are having even in the normal metal a little bit of the superconducting properties. Okay? So this is the picture which I'm just trying to show here. That this is the length scale over which, here it's, the book still didn't discuss these things. But basically you see that the superconductivity is surviving only in the normal metal to the distance Xin. Here I have it differently plotted. I'm just apologizing that this figure is like that X component here and the graph is going in this direction. So X is here and Psi is here, and you are seeing this tangent, hyperbolic, and then it's going to the exponential. And if it would be in the vacuum, then I need to solve it differently, and it should be satisfying this equation that the derivative of that is equal to 0. And also the order parameter is equal to 0 if you're going to the vacuum. So it's a different solution. And there is not an analytical form for that. Okay? But numerically you can solve it. And you see if you're going to the bulk, to the infinity, both of them are coming to the value of equal to 1. Okay? So this is the proximity effect. And it plays an important role that you can have SNS junctions, that even you take two different superconductors and you put something non-superconducting in between, this thing in between starts to behave effectively as kind of the superconductor. And it has a property for superconducting junction. So that would be everything for today. Okay, this is the trick, and this is the main thing. The proximity effect means that the superconducting correlations are leaking into the normal region, and superconductivity in the superconducting side is a little bit weakened. Here we see that here it's suppressed from the value 1, and here it's enlarged from the value 0. Okay, dog?
So in the proximity effect, we don't consider any, if there's magnetic field?
No, then it will be different because we will also have a screening. Yeah, so we will have also that magnetic field, you will get some screening currents, so the proximity will be different. So this solution really means that you take the two guys and you put them together next to each other. Okay?
Okay.
That's it. Čepin, Šišený.
How about if we proximity this superconductor to an accelerator?
Then it would be looking more like this. This solution, that the solution would look like that the order parameter should satisfy also this other boundary condition. And this other boundary conditions means that the normal vector times the gradient of the psi is equal to 0. Okay? So we see that, okay, in our case, n vector is this one. So we see that the partial derivative of x with respect to psi should be 0. And since it's a vacuum, that also the value at x equal to 0 should be 0. So this equation we need to solve. That partial or the derivative of the order parameter with respect to x at x equal to 0 should be 0, and psi at x should be the 0. So it would look like this. It will start, and then it will look like that. And the other case is, so this will be the vacuum. And if it's a metal, then it will be like that. Yeah, I'm using some books, and one is using like that, another like that. And I don't have really time to redo the figures, so one is like that. I'm trying to explain you. Since you are sitting here, you understand it. But, okay, there is inconsistency. One is from one book, and another is from other one. But both, this is from Zirlin notes. These notes are on the Moodle, and this is from the Schmidt book. So it's there, okay? So next time I will tell you something about the interface between the superconductor and the normal metal. And if you are having the phase transition, this is, okay, still questions to that? It's fine? Yeah, so just keep in mind this psi0 which I introduced, this psi0. This has a meaning of the maximal possible Cooper per concentration you can have. You cannot have more, you can have only less. Okay? Good. Okay, so what I want to tell next one. So if you are having the magnetic field in the game, that you know that the transition from the superconducting states to the normal states is the first order phase transition. Which means there is a latent heat consuming, and the two phases can exist next to each other. Imagine you are melting the ice. You have a piece of ice and water. And if the temperature is 0, they are coexisting next to each other. Then if you a little bit raise the temperature and wait a long time, the ice is melting. Or if you cool it a little bit, the water is freezing, right? The question is what happens with the superconductor? In the same analogy, I adjust the magnetic field exactly to the critical magnetic field. Okay? Then I would have regions which are superconducting and regions which are normal metals. Yeah, that's what we would expect. It's like the first order phase transition. They can coexist. Second order phase transition, they don't coexist. It's smoothly changed. Okay? And now in the phase transition of the first order, you can have two effects. Like if you, for example, melt ice, then you normally see that the ice is staying bulky and it's slowly decreasing. But there are other things, for example, that if you come to the critical temperature, they separate into many small pieces, and those pieces are then melting or something like that. It's called a nuke. Or how the something happens is that there firstly appear so many tiny things, and then they nucleate together, and then they join things like that. So what I want to tell you that the process can look like that the material, if you come to the critical temperature, can be happy to stay as it is, and it's slowly disappearing, slowly disappearing, slowly disappearing, and it's disappear. Or it can have other destiny that instead of that, it makes many fractions. The fractions go out of say, and then they are disappearing. And always they are fracturing and fracturing and fracturing and fracturing. You can see like it's happened like that. They're cracking, 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 and then disappearing. Yeah? Can you imagine what I'm talking about? So there are two different processes how this can happen. But whether it's happening in the bulky state or it's a cracking into many pieces and disappearing. And this is telling you, so this guy is trying to keep the surface minimal. This guy is trying to make the surface maximal. The surface between two phases to be a maximal. So surface energy is telling us how the process will look like. If the surface energy is positive, then material would like to minimize the surface. Okay, I will melt because I should, because you rise temperature, you motherfucker, but I will not break. I will do it as much as can because I want to minimize the surface energy. The other guy which has a negative surface energy, you bring him to the phase transition and say, finally, fuck, and he breaks and goes and enjoying that he's braking and things like that, okay? So there are two different things like that. And type 1 and type 2 superconductors are those beasts. One likes to keep as much as possible bulky, and he is not happy. He knows he should go to the normal state, but he will go as much as possible with the minimal contact surface. And the type 2 is opposite. Can you imagine? So this we will do. We will calculate the surface energy of the superconductor, and we will see that it's positive or negative. And we will see that this parameter kappa is telling us which one it is. Okay, so kappa will be the guy who will tell you of that. Okay, good. So next time, surface energy and understanding what is a type 1 and type 2 superconductor, and have this analogy, water and or something what is breaking as a picture. What does it mean, surface energy positive? If the surface energy is positive, you want to minimize the surface of the contact. Like, don't touch me, you know, like. And the other thing, touch me, you know. So that's something like that. Okay, so this is a negative surface energy. You like to maximize your surface because you minimize the energy. Okay? Then see you next Wednesday. My theater parcel.